Good day, everyone, and thank you for joining the first Technology Forum presentation of 2022. I'm Ron Hawkins. I'm Director of Industry Partnerships at SDSC. And once again, welcome. The Tech Forum is a series of presentations by SDSC and its industry partners, and we seek to inform and build further engagements and collaborations through these presentations. We strive to do these on a bi-monthly basis. We're a little behind the curve in developing our 2022 schedule, but I think we've got one we're about ready to announce for April. So keep an eye out for that and stay tuned for more presentations throughout the year. So I doubt it's a surprise to anyone on this call that GPUs have been sort of integral to the deep learning revolution over the last 10 years or so in terms of providing the cost-effective high-performance computing power needed to train deep learning networks, deep neural networks. That said, given that GPUs weren't inherently designed for that task, innovators over the last few years have recognized the opportunity to develop purpose-built architectures that are both performant and efficient for training deep neural networks and related tasks. And we are fortunate today to have one of those innovators available, GRAPHCORE, to tell us about their technology and their journey in this space. And so I would like to introduce Saurabh Kulkarni. He is the Vice President and General Manager, North America for GRAPHCORE. And he's going to take you through a presentation and hopefully answer some of your questions at the end. Saurabh?
Thank you, Ron, for the introduction. Let me start by sharing my screen. Presentation mode. Okay, presume this is visible to everybody.
Yes.
Is that coming out good?
Yes. That's good on my end.
Great, thank you. So good morning, good afternoon, and good evening to all of you, depending on wherever you are. My name is Saurabh Kulkarni, and Ron, once again, thank you for the kind introduction. In my capacity, I run our North America operations for GRAPHCORE. And as a brief introduction to GRAPHCORE, for the benefit of those here who are not familiar, GRAPHCORE started off being an AI processor company with a keen focus on creating a highly fine-grained parallel machine following the MIMD or multiple instruction, multiple data paradigm, with a particular emphasis on accelerating machine intelligence workloads. As you all can imagine, it is not sufficient to just build an efficient AI processor. The software stack that enables developers to use the processor at high efficiency and the scale-out systems that enable users to use the processor at hyperscale are equally important in today's day and age. And that is exactly what we are focusing on. Now, into the second generation of our product, we are fast evolving to becoming an AI processor, software, and systems company. For today's talk, I'm going to be focusing on large-scale AI models and some parallelization techniques that allow us to map those models efficiently on hyperscale systems. I will be using transformer-based language models as the exemplar model type to make the point on several concepts. But please note that these notions can be mostly generalized to other model architectures as well. There'll be some subtle differences here and there, depending on how the model is laid out, but they mostly apply. I will start by framing the problem statement, going over some industry trends we are seeing based on our conversations with key customers and also some noteworthy publications that have come out in this space recently. Then I will talk about some of the challenges involved in running at scale, both computational and also memory-related challenges. That will lead into some commonly used techniques for model decomposition and mapping these TERA-SCALE models onto hundreds or potentially thousands of accelerators. And finally, I will move to describe GraphCore technology briefly and how we aim to addressing some of these challenges in the future and presently as well. I will be happy to take questions at the end. I'll try to leave 10 minutes. And I'll also leave my contact information on the last slide if any of you want to get in touch after this presentation to discuss further. So without further ado, let's jump right in. To begin with, here are some observations on trends and key tenets for designing AI systems at scale that we at GraphCore try to adhere to. First and foremost, and I don't really need to say this, but the rate of innovation in algorithms, model architectures, model mapping and optimization techniques, job orchestration and scheduling tools, MLOps, what have you, continues to remain very high in the field of AI. It makes me feel really good about my job security, at least for some time. With respect to model sizes specifically, it is becoming very clear that TERA-SCALE models will be necessary for superhuman AI. So by TERA-SCALE models, I mean models with upwards of 1 trillion parameters or more. And when I say superhuman AI, I do not at all imply AI transcending human abilities in all functions that require intelligence, but more so the notion of AI surpassing humans in certain targeted tasks, like computer vision or like vision or language in the future. To make training of these TERA-SCALE models economically viable, we are going to have to resort to a lot of algorithmic innovation rather than just maintaining course on current lines of thinking. Equally important will be the need to build and deploy efficient scale-out systems in the data center, because that is the infrastructure that is going to power all of this. And software obviously is going to play an important role in all of this. And the challenges that the HPC world has seen historically will need to be tackled by system architects and designers for AI workloads as well. They are being addressed already. I just foresee that it will become even more mainstream going forward for AI. In all of these conversations, we tend to be hyper-focused on accelerators for AI, but not talk much about general purpose or host compute that is absolutely essential to run the non-AI components of the stack. So when it comes to host compute to AI compute ratios that are deployed in a typical data center STAM, we need to give end users the flexibility to choose that ratio elastically so that they can scale it to their liking, because certain workloads may require more CPU than others. So giving users the flexibility helps them to optimize for costs. Resource disaggregation in this sense becomes very, very important. Next, let's see how the landscape on state-of-the-art models has been evolving over the last years, taking the examples of deep neural networks for language processing. BERT Large, with 340 million parameters when released in 2018, set a new standard for natural language modeling. And ever since then, the transformer architecture with the multi-head attention mechanism essentially took over the language processing domain. Models like GPT-2 and GPT-3 from OpenAI with 1.5 billion and 175 billion parameters respectively, or other models from the likes of Microsoft and Google have continued to push the envelope in terms of model size, and also thereby the compute requirements to train these models year over year, or I should say quarter over quarter, looking at the pace of innovation in this space. And the research community, trust me, is not stopping at this. In the not so distant future, we are looking at models that will break the trillion parameter barrier and much beyond, representing almost an exponential growth in the parametric state that these models will hold. The switch C model is of particular interest. You folks probably saw the publication a little while ago. I will talk about that shortly to make the case. The motivation behind large models, of course, is simply the fact that larger models produce better quality of results. And in the case of language models in particular, large models are more sample efficient. So what do I mean by being sample efficient? In very simple terms, it just means that large models can be trained to a certain accuracy threshold with fewer samples or fewer iterations compared to their larger counterparts relatively. Hence, it is better to train large models for fewer iterations rather than training smaller models all the way to convergence, as is articulated very well by researchers at OpenAI in their scaling laws paper. I would recommend that as a very good read to those who are interested. So while scaling models in the dense regime will continue its course, that paradigm is not sustainable in the long term from a feasibility standpoint. To make the case here, this graph shows the number of flops consumed in a single iteration on a single sequence for a few model sizes based on the transformer architecture. So we have BERT large here, GPT-3, and then 3 other models, representative models with 12, 50, and 200 trillion parameters. Now note that these are not really models that are being used in production. We've just constructed them to make the point about computational budgets. As you can see here, a 200 trillion parameter model consumes roughly 3.5 exaflops to process a single sequence in a training iteration, just one sequence. And a typical training run will entail millions of such iterations with thousands of sequences processed in parallel. Thus, as you can see, if we just simply blindly follow this notion computationally, this is not going to be sustainable. Another way to look at the computational costs, the bloating computational costs for large models, is time to train those models. That is probably a more relevant metric because at the end of the day, the user is interested more in the results after the training and how well the model is trained. But that metric can be a bit subjective as it depends largely on the training objective of the user. But it still is worthwhile to spend time on making the case there as well. Here is a chart from the famous GPT-3 paper as referenced below. If you look at the bar on the extreme right, which represents the GPT-3 model with 175 billion parameters, you will notice that the total cost to train that model is close to 5,000 petaflops per second days. So just think about that number for a moment. Let's say we put a 500 petaflop supercomputer to use to train this model. It means it would take 10 days to train this model from scratch on that massive supercomputer, assuming that we get perfect efficiency or 100% efficiency out of that hardware. But that's not a very practical assumption, isn't it? So let's say 50% efficiency off peak, which is more reasonable. That number is still 20 days for just one instance of a pre-training run on GPT-3. And just to give you an idea, a 500 petaflop computer, supercomputer, based on today's technology, takes multiple data center rows to deploy, and I'm not even talking about the power cost associated yet. So what all of this informs us is that a different approach is required if we are to give ourselves any hope of being able to train TERA-SCALE models efficiently in the future and make them available to more than a select few entities in the world who have the wherewithal to train those models based on today's budgets. So now that I've hopefully made the case for why we cannot continue to operate indefinitely in the dense regime, let's talk about sparsity. Since the quality of results from DNNs is generally proportional to the number of parameters in the model, at least the language models of today clearly show that, one way to scale the number of parameters and thereby model quality is to make these models sparsely activated. So techniques such as sparsely gated mixture of experts will be required to boost the parameter count on the models, but not proportionally increase the computational budgets as well to keep them under control and make these model training regimes feasible. Approaches based on just pure block sparsity or structured sparsity, as some people refer to it, that rely on sparsity patterns in the underlying data itself alone are not sufficient. So I'll not spend too much time on this slide, but here is a high-level architectural diagram representing the switch transformer architecture from Google with the reference below here. It relies on the conditional compute concept, which is very, very interesting in this context. In that scheme, every training sample sees the entire parametric state of only a part of the entire model. In this case, the attention heads. Tokens that are representation of words or a set of words in a language model context within a certain training sample, which can span multiple tokens, are selectively routed to only one of the many relatively smaller fully connected layers that typically form a transformer architecture based on a routing function. Unlike a traditional dense approach where the FCN layer is humongous and every single token goes through that entire FCN layer as it gets processed. So that's the fundamental concept behind sparsity in this context. The model is sparsely activated. There's no sparsity or reliance on sparsity in the data itself. So I just wanted to make that case before we move on. We have talked a lot about compute, but what about memory? Memory capacity needs are dictated by three primary components when it comes to training large models. First is the model weights and the optimizer state. So in the case of Adam, which is a commonly used optimizer here, we use first and second order momenta. And the memory requirement for the optimizer state is actually larger than the weights themselves. And then there is gradients. There is also intermediate activations that are temporal in nature. They don't need to be persistent. And also activation stashes if we do recomputation. I will not talk about recomputation today, but these are the three primary components of memory occupancy. Which all again is pointing towards the fact that DRAM capacity and not necessarily DRAM bandwidth has the potential to becoming a bottleneck, is already becoming a bottleneck when it comes to these large models. Bloated memory costs can adversely impact the TCO for any AI solution, which is why we need a well-designed memory hierarchy that can result in significant cost and power savings. Moving on, let's talk about some parallelization schemes that users generally employ to map these very large models onto hardware accelerators with a limited amount of memory. We generally resort to two types of parallelization paradigms. The first is model parallel, and then we get to data parallel. Let's start with the first scheme. So this is my feeble attempt to depict an oversimplification of the complex job of a compiler or auto partitioner to map a neural network to a bunch of AI accelerators. The green circles along with the solid black lines represent a neural network composed of 8 layers in this case. When we talk about model parallelism, we generally refer to 2 axes along which we can break the model apart. One is the layer axis, which assigns different layers to different accelerators. The other dimension is the tensor dimension, where a single layer or perhaps a set of layers have to be further broken up to map to more than one accelerator. This is necessary when the layer is too large to fit in the memory of a single accelerator, which will be the case as we start talking about trillion parameter models. In the case of very large models, we generally have to resort to a scheme that uses both these approaches. That is what this picture is trying to show here. The red dotted lines show the layer-wise split, so the vertical split. Oftentimes, when we decompose the model in this fashion, we employ pipelining to ensure maximum utilization possible on the hardware resources. Hence, I'm calling this as the pipeline model parallel dimension. The blue dotted line shows the tensor sharded or tensor model parallel dimension. So as you can see, this is a scheme to divide the model into 16 partitions or 16 accelerators that are represented by the yellow ellipses. Needless to say, load balancing amongst all of the accelerators is a big concern. This is a very simple case. We really in practice deal with a lot more accelerators and much more complex models. Models with highly regular structures like transformers. In those cases, the task of load balancing is a little easy, I would say, since there is a reasonably clean way to shard the transformer layer evenly along the attention head dimension, because all the attention heads are generally equal in proportion. And the layers are also very, very uniform, at least for the transformer piece of it. The embedding layer can be a bit problematic, but that's a corner case. But this is transformers. That may not necessarily be the case for, let's say, convolutional neural networks, where there is a lot more non-uniformity. There is also concerns on blowing up the communication costs in model parallel scenarios. More to come on that on the next slide, which talks about a little bit about data parallelism. So taking the same example from the previous slide, let's say we had many more than 16 accelerators at our disposal to throw more compute at the problem and accelerate training. That's where data parallelism will come in handy, where we simply stamp out replicas on multiple accelerator groups. And this picture shows that same model parallel scheme, but now replicated multiple times. This creates what we generally refer to a hybrid parallelization scheme comprised of tensor model parallel, pipeline model parallel, and also data parallel implementation. Communications overhead becomes an important consideration. There are two primary sources of that overhead. One is due to the exchange of activations in tensor model parallel schemes, and also in the pipeline parallel schemes, lesser so in pipelining generally. The second source is the overhead of gradient reductions amongst the various replicas to perform a consistent master weight update at the end of every mini batch iteration. This obviously varies greatly with the model type and the number of layers and a few other parameters. It can become a bottleneck to the extent that the efficiency we get out of a large scale out can reduce to less than 50% even if we are not very careful. So if we are able to introduce some level of overlap between computation and the communications, we can greatly reduce the time to train those models by trying to eliminate to a large extent the communication overhead. I will not talk in depth about this particular aspect today, but if folks are interested, we can have an offline discussion. An often overlooked aspect of training these mega models is batch size. In a typical mini batch SGD training run, the problem with increasing batch size unscrupulously is that the number of gradient updates that we are allowed reduces with the global batch size for a given number of tokens that the model is trained on. So there is a global batch size constraint, as is apparent from this table that again I have taken from the GPT-3 paper that shows the progression of optimal batch size from the GPT-3 small model with 125 billion parameters all the way to GPT-3, the large one, the 175 billion parameters one that has an optimal batch size of 3.2 million parameters. So obviously batch size does not scale. Hence, larger model replicas are generally favorable, and more certainly any architecture that takes a heavy dependency on increasing the batch size to improve the T-flop efficiency on the underlying hardware will be at a distinct disadvantage. given this batch size constraint, because it cannot be increased indefinitely. So what does this all mean to the buildup of a typical data center systems in the future? Here's what our view is. Besides the footprint of regular compute, storage, and networking stamps to service the needs of traditional applications, we are also looking at a significant portion of the data center space allocation going towards AI compute in the future. Some of the core capabilities that govern the deployment and lifecycle management of general purpose compute infrastructure will be just as important for AI compute going forward. Different models have different needs for host compute. I think I made this point earlier, but depending on the task at hand that runs, the portion of the task that runs on the CPU, it behooves us to ensure that we offer flexibility and the ability to independently scale host side resources with accelerator resources. Another key requirement is that users demand automation. It may be practical to manually place models on systems with 4 or 8 accelerators for 1 or 2 use cases. But when we are talking about supercomputer scale systems in the data center, comprising of thousands of accelerators, automation is a must. So we cannot overlook that aspect. So with all of that context, I would like to spend the rest of this session talking about GraphCore technology. But before that, let me spend some time on some core tenets of the GraphCore design philosophy. So front and center on that is we are all about designing for scale. Everything that we do starts with the outcome that we want to achieve at the end of the day, which is designing or deploying systems at large scale for some of our largest customers. Large distributed on-chip SRAM minimizes data movements to and from external memory. I will have some more details on this aspect later on. But what this allows us to do is extract better performance per watt. And that is an important parameter because power costs are going to be increasingly dominant in systems of the future. And the other benefit of a large on-chip SRAM is that it facilitates exploitation of data locality and relieves the pressure on external DRAM bandwidth, which leads to generally better economics due to low-cost memory that we can deploy as compared to HBM that that is much costlier. And finally, we also strive to, in order to address the communications cost overhead that I talked about, we try to maintain a more balanced interconnect at the rack scale. I will, again, in today's session, I will not have a lot of time to talk about our interconnect solutions, but again, worthy of an offline discussion if anybody is interested. So let's dig into the technology a bit. Keeping in mind the scale and flexibility requirements from our most demanding customers, we decided to take a highly modular approach towards building scalable systems for machine intelligence. Let's start with exploring all those building blocks one by one. The smallest unit of compute comes in the form of what we call the Intelligence Processing Unit, or IPU in short, built in 7 nanometer technology. This is our 2nd generation chip and is a behemoth of sorts. One of the largest chips manufactured on this node, if not the largest. It packs in about 60 billion transistors on the die. This is a massively parallel MIMD machine with 1,472 independent processing cores. Each of the cores has a tightly coupled SRAM, 624 kilobytes per core, that can be accessed in a highly deterministic fashion. So the number of cycles to access any area of memory is fixed. The core itself is barrel threaded with 6 worker threads scheduled on a round robin basis. Each core, or tile as we call it, has a highly efficient floating point unit capable of performing IEEE FP16 and FP32 operations in today's generation, leading to a cumulative peak performance of 250 teraflops per second per chip. The total amount of SRAM that is distributed across all these tiles per chip is close to 900 megabytes. This on-chip memory is accessible to the tiles at a total bandwidth of 47 terabytes per second for data operands. If you think about it for a moment, that's an order of magnitude, or actually close to a couple of order of magnitudes than some of the fastest HBMs we see today. The tiles need to communicate with each other, and that is accomplished via an on-chip exchange fabric that delivers up to 8 terabytes per second of total bandwidth with non-blocking data transfers between tiles that are supported. The hardware parallelization scheme that we rely upon is the bulk synchronous parallel paradigm. It comprises of a data exchange phase, followed by a computational phase on all the tiles, and then a synchronization barrier to keep all the tiles in sync. As some of you may recognize, the BSP paradigm has been historically used as a software programming model for highly parallel graph processing or big data algorithms. So we are taking a cue from that. And besides these goodies that are essential for on-chip compute, the IPU also has IPU links, which are based on PCIe Phi in this generation. They enable connectivity to other IPUs to form a network of IPUs to process the parallelization schemes that I have already talked about. The total bandwidth coming out of every single IPU is close to 320 gigabytes per second full duplex. The host connectivity is provided by 8 PCIe Gen 4 link. We assemble 4 of these IPUs on a board in a 1U chassis, which we call the IPU-M2000. This is the smallest commercially available unit that we sell to customers. Along with the 4 IPUs, the IPU-M2000 also has a proxy host chip that we call the gateway, which besides providing boot functionality to the IPUs and connectivity to the host subsystems in a typical data center environment, also has DDR channels, which are essentially avenues for us to open up access to bulk memory for the IPUs. Besides the on-chip SRAM, we also support external memory in the form of DDR that is attached to this gateway. We call this exchange memory, and this is what allows us to target much larger models that can be accommodated on the on-chip SRAM. I often see questions about how we plan to compute with other contemporary architectures that employ higher capacity HBM stacks. Exchange memory is our answer to that. We use exchange memory to store the optimizer state for modest size NLP models currently. For very large models, we will expand that capability to hold the entire model parametric state in that attached DDR. In summary, a memory hierarchy that is comprised of very high bandwidth on-chip SRAM and high capacity off-chip SRAM gives us a significant TCO advantage in this era of mega models. We are hard at work on fine-tuning a set of programming APIs that will allow developers to seamlessly access streaming memory in their applications. We have released some examples recently in public domain as well. And we are also hard at work to automate a lot of these model decomposition activities. The gateway chip also has 200 gig Ethernet links that are used to provide inter-rack connectivity because that is essential to build scale-out systems. These gateway links, as we call them, form independent switch network planes which offer a high degree of scalability as well as reliability and fault tolerance. This being commodity Ethernet, switch costs are also lower than proprietary solutions like, let's say, InfiniBand. And finally, the IPU-M2000 chassis will have an RDMA-capable 100 gig NIC that provides connectivity to the host, like I mentioned earlier. This link to the host forms the basis of our disaggregated architecture for scale-out systems. So in summary, this box packs about a petaflop of peak FP16 performance in a single U. which is quite significant. To complement that on-chip memory that I talked about, we also can support up to 256 gigabytes of exchange memory per chassis in a 1U form factor. That is the gateway attached DRAM. So how do we scale? Here is our modular approach to designing these large scale out systems in hyperscale environments. Start small, but go big. Starting with our smallest unit of compute, the IPU-2000, we can seamlessly scale to hundreds of IPUs organized in IPU-PODs, and that will scale to thousands in the not so distant future. The current architecture supports a maximum scale of 64,000 IPUs, which realistically is not something that we foresee happening anytime soon from a commercial deployment standpoint, but we have the technology to support that. This slide tries to depict our disaggregated approach towards resource allocation and management in a typical data center setting. On the top left, I'm showing general purpose compute resources which can scale elastically. They can come in the form of VMs or bare metal instances or just some services installed by the customer on-prem. Support for multi-tenancy on the host side is thereby just a natural consequence of the architecture and can be achieved by running virtual machines and providing the usual isolation guarantees. Especially useful in a hybrid cloud environment. In theory, a customer could leverage general purpose compute, infrastructure resources, and other services from a large public cloud service provider like AWS, for example, use a performance storage solution from a different cloud provider, like Oracle or Dell EMC, and then finally use GRAPHCORE IPUs from us for their AI needs. So what this is trying to show is that we offer a very, very flexible architecture that is rooted in network-based resource disaggregation. So now, going back to my earlier description of the various model decomposition strategies, this is how it all comes together in an actual example, how a large model is mapped to an IPU-POD system. Now, I've not been able to do justice in the limited amount of real estate that I have in the slides to actually depict lower level details, but I'll try to explain. The tensor shard dimension that I was talking about is, in this example, mapped to a rack. Now, this rack is a set of IPUs that are interconnected via a 2D torus based network in today's architecture, and that's depicted in the box with the red border. The layers are laid out across racks, so that becomes the pipeline parallel dimension. So the horizontal blue lines depict that dimension. And then finally, let's take as an example, one model replica spanning an entire data center row comprising of multiple racks. We can create multiple such replicas that span multiple data center rows to create a data parallel regimen that will allow us to efficiently use the scale of close to an entire data center if a customer so chooses to run large models efficiently. So that's what the logical view, this is where the logical view and the physical view of things kind of combine and make these things possible. So I've talked a lot about parallelism strategies and efficiency and whatnot. All of that looks great on paper. But when it comes to actually putting all of this to practice, it essentially comes down to the compiler stack and the automation frameworks for doing the partitioning of these workloads among multiple accelerators. So the role of these software components cannot be overlooked in all of this. Implementing these schemes manually is always an option, but it's not at all scalable. Engineering teams can invest in manual placement of parts of a large model onto individual accelerators for one or maybe two model variants for maybe a couple of experiments. But beyond that, it is just not practical for the human or set of humans to do this complex task. So this slide shows the progression in the compute scale which the compiler has to deal with, going from a single IPU all the way to the theoretical limit in this generation, which is 64,000 IPUs. As you can see, each incremental modular component has different characteristics when it comes to the core count, for example, or the interconnect topology connecting all of these elements, or the efficiency at which those compute elements can actually operate. All in all, what this slide is trying to depict is that the compiler needs to comprehend all of these constraints. The compiler and the auto-partitioning framework has to comprehend all of these constraints, and then do a reasonably good job of load balancing across all of these chips to ensure that we extract the most amount of efficiency, which is all telling us that it is going to be all about the software frameworks going in the future to allow us to use IPUs at the scale. Let's change tracks a little bit because multi-tenancy is important. This slide has nothing to do with machine learning algorithms, but is important nevertheless because managing multi-tenancy at scale is enormously important given the size of these deployments. This is especially true or important in the case of cloud deployments. So this should not be a surprise. Let's look at the multi-tenancy options that our architecture facilitates. Listed here are 3 possible scenarios, but countless others exist. And given the flexibility in our architecture, I'll definitely not be able to go through every single one of those. Multi-tenancy, by the way, applies to both the host side resources and the IPU side resources. For host side multi-tenancy, isolation can be achieved either by running instances of our popular software stack in virtual machines or containers on the host. Scenario 1 shows a single host server paired with a pod 64, IPU-POD 64 in a multi-tenant environment. As you can see, the host server has 6 different tenants, which can either be VMs or container partitions that map to variable number of IPUs in the rack in the leftmost column. Scenario 2 is again a single host server, but this time that host server is single tenanted, meaning that it only has one partition, and is mapped directly to an entire pod 64. So this is a completely single tenant solution in this context from a binding perspective. And then finally, scenario 3 is a multiple host server scenario that shows a situation where the customer workload requires more CPU resources than just one server. So let's say 4 servers, and those are mapped to 2 pod 64s, and we support such schemes as well. Let's turn our attention now to our software stack. As all of you can very well appreciate, and I'm repeating myself, but building the highest performing hardware infrastructure for the application stack is necessary, but is not sufficient to attract developers to the platform. Hence, we have invested heavily over the past few years to enable key components of the stack, ranging from high-level machine learning frameworks and APIs and libraries like TensorFlow, PyTorch, and Keras, to resource management and orchestration frameworks like Kubernetes, to make the life of the developer easy, because they are going to want to operate in an environment that gives them the best level of abstraction when it comes to writing their models. At the heart of our popular software stack is our graph compiler that takes graph representations from various high-level frameworks like TF or PyTorch, and takes them through intermediate representations or IRs and several transformations, and produces machine code that can be executed on the IPU to aid easy graph transformations from higher level constructs or frameworks, and also to offer developers better customization options. We also provide a rich set of graph optimization libraries, both for linear algebra kernels, which are the heart of DNN compute, and also kernels for efficient communications primitives. And speaking of communications libraries, GCL or GraphCore Communications Library is the component that allows us to efficiently implement these precompiled collective communications primitives like all reduce or all gather, all scatter, that are a key ingredient in modern day model parallelization and decomposition schemes. There is also the hardware resource management piece, wherein we support open source frameworks like OpenBMC for hardware management, and there is also visualization and profiling tools like Grafana or Prometheus that are also supported on our stack. So how are we enabling developers? This is just links to some GitHub repos where we have a lot of documentation, public examples of models that we have enabled in PyTorch as an example, or TensorFlow. By the way, we have recently added support for PyTorch Lightning, and also Keras has been around for a while. And then there is also a model garden that we publish that is essentially a collection of pre-canned models that are specifically optimized for the IPU that customers can essentially just pick from the model garden and either use as reference or just take them directly to production if they meet their needs. We also have a developer portal that has a wealth of information about our SDK, some tutorials, how-to videos, a link to some pre-recorded webinars that go over both our hardware and software, a bunch of research papers, some podcasts, and all in all, kind of almost like a one-stop shop for developers to go and explore our technology, especially from a software stack standpoint. And then finally, this is going to be my last slide. I'd like to go over the summary and some key takeaways that I hope you all take from this talk. So first and foremost, the IPU's fine-grained parallelism and the distributed nature of the compute that we enable unlocks a new paradigm for emerging AI models. We like to pitch our platform not just an attempt to copy something that's out there, like Ron mentioned earlier, GPUs. We are not in that business. We are not attempting to clone GPUs. What we are trying to offer is a platform that allows machine learning scientists, researchers, practitioners to innovate. The IPU-POD systems that we are making available offer elastically scalable and cost-effective hyperscale options to be deployed in data centers. And finally, we offer a powerful platform that fosters innovation in this age of trillion parameter models that we are about to embark on. So the call to action here is come, innovate with us. We are here to support you in all your AI needs, and would love to learn more about all of the groundbreaking work that you all are doing to advance the use of AI in multiple fields. So with that, I come to the end of my talk. I'm leaving this slide up with contact information for myself and also Ryan Emmerich from Applied Data Systems, who has been a key partner in facilitating all of this for us. So thank you.
Okay, thanks everyone who stuck around, and we will we'll adjourn this one. And like I said, keep on the lookout for the next presentation in April. Thank you.
Excellent. Thank you all.